So let's recall quickly where we're standing. And last time we reformulated the Frobenius splitting via local Serre duality. And we arrived at theorem 3. So it was understood that there was an isomorphism that was denoted iota hat from the Frobenius push forward of the dualizing sheaf to the power 1 minus p, and the local morphisms from Frobenius push forward of the structure sheaf to the structure sheaf, where the possible splittings live in global sections of this sheaf. And we say that a section phi splits X if iota hat phi splits in the usual sense. So once again, we reformulate conditions on the Frobenius splitting in terms of sections of this power of canonical line bundle. And then theorem 3 says that if X is smooth, then this iota hat identifies the evaluation epsilon from here to global sections with tau hat from the push forward of the dualizing sheaf to the structure sheaf, and in local coordinates this tau hat looks like it takes function times the local generator to the trace of this function, and the trace we also discussed last time, but maybe I will not discuss it once again. We say that phi splits if tau hat of phi is 1, and if X is proper, then there are only constant global functions, and so then phi splits if the p minus 1 product of p minus first powers of all the coordinates in this enters with coefficient 1 the expansion of phi at any point in our variety. Well, maybe I should say that this times dt1 dtn to the power 1 minus p. Okay. Yes, but by the well, shall we recall the definition of trace, or not necessarily? So yeah, it took coefficients of this sort times t to some power divisible by p, and then sent it to the coefficient of no. Okay, and then after that we started proving proposition 3. Then again x is smooth, dimension of x is n, and there is a section sigma of the anti-canonical bundle, and we're going to test if p minus first power of this section splits. Okay, so we could take phi equals to p minus first power of sigma, and the proposition formulates conditions for p minus first power of sigma to be a splitting. So suppose we have a section with zero divisor y1 union so on, yn union z. So here y1 and so on, yn are smooth transversal, well, smooth divisors intersecting transversally at some point x, and z is somewhere far away, so x does not lie in z. Okay, so it looks like this. Here is our point x, and z is somewhere away. Okay. Okay, and then if we take p minus first power of sigma, then it splits x compatibly with all those smooth divisors intersecting transversally. And this we proved last time, and there was also some converse statement which we didn't have time to prove, that if sigma to the power p minus 1 splits x, then the zero subscheme of sigma is compatibly split, and reduced. Okay, so I mean, sigma could have possibly some multiple divisors. Yeah, like for example, we could have a section of omega inverse p1 that vanishes at some point with multiplicity 2. Yeah, because we know that this is O p1 of 2. So good situation is a section with two zeros, two distinct zeros, like this. Then this is y and this is z, and this splits. And bad situation is a section with just one zero, but with high multiplicity 2, and this does not split. That's bad. This is good. Okay?
So the good thing about the first one is that this is the best thing.
Yes.
Is that there is no z.
No. The bad thing is that the divisor is not normal crossing simple divisor, because it has multiplicities. It's not reduced. It's a thick point. The corresponding zero scheme has nilpotence. So this is not allowed. So this should be multiplicity 1 smooth divisors with transversal intersection. Okay? Like here. So this is not 2, this is z. Okay, so let's prove the second part. Let's take y, a component of the zero divisor, and x, a smooth point of the reduced thing. Yeah, so for example, here it's a point with multiplicity 2, but we kill the nilpotence, we get just one smooth point, and this would be our x. Okay, so choose local coordinates, t1 and so on, tn, such that t1 equals 0 is the equation of our reduced component around this point x. Now write sigma is t1 to some power, yeah, because we took reduced, but it might be, the y itself might be not reduced. So it might be divisible not by t1, but to t1 to some power, like t1 to the square in this example. And then g of t1 and so on, tn, sorry. And then dt1, dt and inverse. And it's locally around x. And g of t is not divisible by t1, so it's that does not vanish at x. M is the order of vanishing, and then we know that this splits x, and it means that the coefficient of t to the power p minus 1 in t1 m times p minus 1 g to the power p minus 1. Yes? No, m cannot be 0 because it does vanish. But we would take the zero divisor. We would take our point x at some component of the zero divisor.
Could be that g vanishes at the point.
No, but we don't, well, we choose a point this way. Okay? So G cannot vanish identically along this component, otherwise this order will be bigger than M. All the vanishing is absorbed into this for first factor.
Okay. That sigma is equal to, say, T2 times this dt1.
Yeah, but we take, maybe I should, yeah, I said that X is a smooth point. So it's not at the intersection. It's a smooth point of, so this is our Y. And we cannot take point x here. We can only take it here. It's a smooth point. It cannot be at the intersection with some other irreducible component.
Okay, I just do not get why m is strictly positive.
Because we know that it's a zero divisor. So, and T1 is the equation of one of the components.
Okay, yeah, I see.
Uh-huh. It is just one component of the zero divisor, but without nilpotence. We are going to prove that it is without nilpotence anyway, but in principle it could be like in this case. But then it would not be a splitting. So that's what I'm trying to prove now. So this coefficient is not zero because of the splitting. But since this coefficient is not zero, it necessarily implies that m is just 1. Okay? And also it implies that the splitting is compatible with y. And also it means that the scheme y is reduced. And there's some nice fact that maybe we will not prove it, but maybe it's the most useful thing you should carry out of today's class. So x is smooth. Y is a divisor, even a Cartier divisor. And y is generically reduced around this point, smooth x. Okay? Implies that y is reduced. So scientifically speaking, it's some consequence of Cohen-Macaulay property. So since it's a divisor, so complete intersection in a smooth variety, it's Cohen-Macaulay. And then if a Cohen-Macaulay variety is generically reduced, then it's necessarily totally reduced. And that's a very useful fact that you should remember from today's lecture. Okay? So we know that it's locally reduced, around all smooth points. But then it means that around other points it's also reduced automatically. Okay. So there we are. You see that the zero scheme of splitting section of the anti-canonical line bundle is necessarily reduced. Okay, let me formulate a couple more general properties, and then maybe in 10 minutes we are ready to go to flag varieties. So these properties are some, again, compatibility properties with extra divisors. So we will say that given an effective Cartier divisor, D in X and a section sigma it's a canonical section Right, so these are functions with poles of order 1 along D. In particular, function 1 is such a function, and this is the canonical section sigma. Okay, we say that X is D split, Frobenius split, if there is an O linear map psi from the push forward of Frobenius push forward of OXD to OX. Yeah, you see, the OXD contains OX, yeah, via this section. In particular, the Frobenius OX is contained in here. And you may restrict this psi to obtain a morphism from Frobenius push forward of X. And this must be a splitting, a Frobenius splitting. So if this is true, then you say that X is D-split. Okay? So if some Frobenius splitting extends to a morphism from functions with poles on D, then we say that X is D-split. Yeah. Okay. So what should I write? Such that psi restricted to OX is Frobenius splitting. Okay, and if we have a subvariety y in X, then it can be compatibly D-split. So usually the condition was that this splitting preserved the ideal of y, and the same is true. Now it preserves the ideal of y twisted by D. Now let me formulate the next theorem for that if X is smooth and D effective divisor, then a section of canonical bundle to the power 1 minus p twisted by negative D gives a D-splitting if tau hat of phi sigma is 1. And that's just like in theorem 3, the same reformulation. And then well, it follows that if X is split by some section of canonical bundle to power by minus p, then X is D-split for D, the zero divisor of phi. And finally, phi in the section of p 1 minus pth power of canonical line bundle splits X compatibly with the divisor D. Maybe it's some deprimed, something different. So if we have some other divisor, then this splits compatibly with other divisor. If phi gives 1 minus p, sorry, p minus 1 times d, splitting of x. Okay. Yes.
In B,
Yes.
that X is D split for D prime equal to 0.
Oh, sorry, it's d prime split. Yes. And the analog of proposition 3 for D splittings is proposition 4. So X is proper, smooth, dimension is n. And again, we have a section of the inverse canonical bundle with 0 divisor y1 plus so on plus yn plus z with the same conditions that those are smooth transversal at the intersected point x, and z lies away from their intersection, just as in proposition 3. And then we say that the p minus first power of this section defines a p minus 1 times z splitting of x compatible with all yi. Okay, so this is an immediate generalization of what we had in theorem and proposition 3. And now let me explain a straightforward application. Why did we need this notion? So for flag varieties, which we will turn to in 5 minutes, we'll have ample line bundles O lambda, and here lambda will be some dominant weight, but it's not necessarily regular dominant weight. So it could be some linear combination of fundamental weights with non-negative coefficients, but some coefficients may be 0. So d1 may be equal to 0. And then the corresponding line bundle will not be ample. It will not give rise to a Plucker embedding of the flag variety. So the flag variety will project onto some partial flag variety fundamental weights. And this one will embed into projectivization of V lambda dual, something like this. Okay, so once again, the corresponding lambda O lambda line bundle is not ample, and so, in the very beginning, I proved that in case of Frobenius split varieties, if some bundle is ample, and so if you take its high power, it does not have any higher cohomology. But in case of Frobenius splitting, already this bundle itself does not have higher cohomology. Okay? But in our applications, we will encounter some line bundles which are not ample. And so we cannot immediately apply to them this first application. But with this more advanced notion of desplitting, we will be able to conclude that still the higher cohomology of O lambda vanish. Okay, so let me explain this. It will be theorem 4.5. Yes. No. So after I explain this theorem, we will turn to study of flag varieties, and then till the end of this class, we will study flag varieties. And our utmost goal will be to prove that flag variety is Frobenius split, and then we will deduce that all the higher cohomology of all the dominant. Sorry, I misunderstood you. What's the question? And what's the question?
You don't need to prove them separately because they are analogs of what we
The proof is the same as for theorem 3 and proposition 3. I'm sorry, what I want to say is that assume X is proper and Frobenius split and even d-split for some divisor. An effective divisor. L-line bundle. So in our first theorem, we considered ample line bundles. Now we do not assume that L is ample anymore. We only assume that L to some big power is generated by global sections. Sometimes it's called semi-ample. Then first, the higher cohomology with coefficients in L all vanish. Second, there is restriction morphism from global sections of L to the global sections of Y with coefficients in L is surjective if Y is compatibly d-split. And we also have to assume that O of D is ample. In fact, a divisor and O x of D is ample.
What is semi-ample?
Semi-ample is some terminology you don't need to remember. It means that some power is generated by global sections.
So L is...
we assume almost nothing about L, only that it's not very negative. But we assume that it is d-split with respect to some ample divisor.
Okay.
So L itself is not interesting, but in case of flag varieties, everything will be not just split, but d-split for some anti-canonical divisor.
Is every effective divisor, does it give rise to an ample?
No, not necessarily, because just consider like this, some projection onto partial flag variety. Yeah, in this partial flag variety, you may take a hyperplane section, which is very ample, and then take its preimage in this full flag variety. And this will be certainly an effective divisor, but not ample, for the same reason, because it will give rise to map into project space, which is not an embedding. But this extra divisor in case of flag variety will be really very ample. It will be anti-canonical, very ample divisor for flag varieties. Like, for example, for P1, this D will be some, well, twice some point. But L itself, you can take just OX. Okay? And then in principle, it does not follow that, from our previous knowledge, that higher cohomology of the structure sheaf on P1 vanish. Well, we know this elementarily from half a year ago, but we don't know this from general nonsense about Frobenius splitting. Okay, but if it's extra D Frobenius split, then it follows that higher cohomology of structure sheaf vanish.
But the structure sheaf itself is not ample.
Absolutely, no. So let's prove this theorem. Let me recall. And in a sense, the proof is almost the same as of theorem 1. But only this divisor D interferes. So we will prove that the higher cohomology of L is a direct summand of the higher cohomology of X with the twist L to the power P to the power N. N is some just arbitrary positive integer twisted by P to the power N minus 1 plus P to the power N minus 2 plus so on plus 1 times D. Okay. And this is 0 because you have some semi-ample line bundle and are twisted by something high and very ample. Okay? So this is generated by global sections, and so you just take some constant, some trivial vector bundle, you're twisted by this very ample divisor, and the higher cohomology vanish, and there you are. So we only have to prove this splitting, and well, we have the splitting psi from. Pardon me?
I is positive.
Well, no, it's true for arbitrary I, but for I positive, yeah, right. So this splitting is always true, but vanishing is also only holds for positive I. So the Frobenius push forward of OXD to OX, it's our psi, and this the D-splitting, it means that the identity tensor psi splits the identity tensor of Frobenius push forward of psi, of sigma, sorry. And sigma was, here it is, yeah, it's still here. This is the same meaning. Okay, and this map is from L to L tensor the Frobenius push forward of OX of D. Okay, And
What is
for with ds, it's called sharp. For sharp is the canonical map from OX to Frobenius push forward of OX. So because of this splitting, it means that the ith cohomology of identity tensor Frobenius push forward of sigma Frobenius sharp from the ith cohomology with coefficients in L to the ith cohomology of X with coefficients in L tensor Frobenius push forward of OX of T. So this is split and hence injective. Okay, and now we just iterate. So we have ith cohomology of X with coefficients in L tensor Frobenius push forward of X of D equals ith cohomology of X with coefficients in Frobenius push forward of this okay, and this is equal to the ith cohomology of X with coefficients in Frobenius push forward of L to the power P of D, and this is equal to the ith cohomology of X with coefficients in L to the power P of D. Okay, so in other words, we obtained a split embedding from ith cohomology of L into the ith cohomology of L to the P twisted by D. And now just iterate. Iterate to obtain this. Okay, there we are. So finally, all the abstract preparation is done with, and we can move to applications to flag varieties. So let's go there. And maybe just a quick survey. So do you know about flag varieties, like Brouillard decomposition? Shuai? No, Leonid? No? Mark? Vanya? Yes, Sergey? So let me give some definitions, but take it easy. So when I say G, I mean SLN. And when I say B, I mean upper triangular matrices. But 0 below diagonal. So when I say U is the radical of B, unipotent radical of B, and it's the strictly upper triangular matrices. Okay. When I say T, it is the diagonal matrices. What else can I say?
Сейчас, в смысле, B может быть негативным.
Pardon me?
B могут быть негативным.
No, it's a subgroup. It's a subgroup. TT is also a subgroup. Yeah, also P, thank you, yeah. It's called parabolic. Subgroup. So just, it's any subgroup containing B. But there are only finitely many such subgroups, and they all look like block upper triangular matrices. Like this. Yeah, we will not need Levy subgroups in this discussion, but in principle, Levy subgroups are generalizations of this torus, so it's block diagonal matrices. Huh? Block diagonal. 0. If it's 0 only below, then it's parabolic. If it's 0 below and above, then it's Levy. And what else? Well, the group G acts in an adjoint way on its Lie algebra. Lie algebra is just all matrices, and again, traceless, yeah. And again, you have upper triangular or strictly upper triangular or diagonal. They are Lie algebras of those subgroups. And in particular, we have this diagonal called Cartan torus. In fact, this B is called Borel subgroup. So this is called Cartan. And this Cartan torus acts in the adjoint manner on the Lie algebra G, and the whole algebra splits into direct sum of eigenspaces. So, for example, the Lie algebra of T itself is the 0 eigenspace because it's a commutative group and commutative Lie algebra, and all the rest eigenspaces have multiplicity 1. So it's direct sum over so-called roots. And all the spaces are one-dimensional. And among the roots, there are positive and negative. So the positive roots, they appear in Borel, and negative roots appear in the opposite Borel subgroup. Maybe I should also introduce.
Do we fix one Borel subgroup?
Yes, let's fix one. After we fixed it, there appears the notion of positive and negative roots. The positive roots appear in the Borel, and negative roots appear in the opposite Borel, B minus. So they are lower triangular matrices. The same applies to Lie algebras, yeah, but the Lie groups as well. Okay. Now, the corresponding subspaces for the case of SLN are just the usual matrix elements, and alpha is well, let's say epsilon I minus epsilon j. So if I is bigger than j, sorry, I is maybe smaller than j, means that alpha is positive. And if it's I is bigger than j, alpha is negative. Now there is this Gauss, whatever, method or decomposition. well, maybe I shouldn't say decomposition. And Gauss method implies what is called Brouwer decomposition. Namely, the so-called while group. The while group is absolutely the normalizer in our ambient group of the torus, modular torus itself. But in case of SLN, it it is the symmetric group Sn, and it embeds into GLN, not into SLN, just as permutation matrices. But you see, they may have determinant -1, plus or -1. So they do not embed into SLN. But still, then this Brouwer decomposition says that the whole group G is the disjoint union of double cosets of Borel subgroup over these permutations like this. And say, Lenny, do you know this fact from, how do you mean? I think you should have known this, say, in your first year algebra, linear algebra. Know that if you multiply by Borel subgroup, but by the upper triangular matrices on the left or on the right, you make some elementary row operations or some elementary column operations, and then you can reduce any matrix to any invertible matrix to the just permutation matrix by performing elementary row and elementary column operations. So you just 3 years ago you should, yeah, right. Mm-hmm. And then it holds true for arbitrary. Yeah, I didn't say what is G more general. Maybe I should say it finally. G, semi-simple Lie group. So, for example, G could be also SON or SP2N. And in fact, well, there are also products of groups, but there are some indecomposable simple groups, and then there are only just 5 more. There are 5 exceptional groups called G2, F4, E6, and 7, and 8, and nothing else.
Значит, полупростая. У нас на теории инвариантов полупростыми называются, когда все элементы полупростые.
It means that semi-simple means that it's more or less direct product of simples, and simples meaning having no, just as in usual group theory, no normal subgroups, except for central. For example, SLN does have center. It's a finite subgroup. So no normal infinite subgroups.
То есть это другое значение.
Yeah. Yeah.
Does this theorem make sense over finite fields?
Oh yes, yes, or arbitrary fields, even over integers. Yes, all those groups are defined over integers.
You just said something about infinite subgroup over finite fields.
So what's the meaning of algebraic, you ask, or what? There is a notion of linear algebraic groups, and then the whole theory works as, say, for compact Lie groups. But then you can take their points with coefficients and finite fields. And then there is the basic theorem due to Chevalier. If you take a simple adjoint group, then it's group of points with coefficients and finite fields is simple, just as an abstract finite group, with just a few minor exceptions, like say if you take SL3 over field F2, then it's not simple. But unless your field or rank is very small, that's necessarily just absolutely simple. Well, SL2 is not good, but it's PSL. In general, you should consider PSL. For example, PSL 2F7, that's the order 168, and it's the automorphism group of this curve you didn't solve in your home assignment. Yeah.
I have a dumb question. Like for a finite field, classification of semi-simple groups is the same.
Yeah, they're all defined over integers, but there are some forms. For example, there are Rie and Suzuki groups that are sort of defined over like f square root of 2, something like this, or square root of 3. Well, it's sort of because over F2, in characteristic 2, I bet you wouldn't be able to distinguish symplectic and symmetric bilinear forms. For this reason, SP and SO, in fact, they are different, but they are very, very close. So, and there is a Frobenius morphism from any group to itself, but for symplectic and orthogonal group over F2, this Frobenius morphism factors through, there is SO like 2n plus 1 F2, and it goes to SP to n F2, and it goes to SO to n plus 1 F2, and this composition is Frobenius, but there is some sort of square root of Frobenius. So I mean, how to say, in this situation I just erased, there's nothing well to speak about. But in case it's n equals 2, then this group is self-dual. So SO5 is, well, up to some cover as SP4, and then there is the notion of the square root of Frobenius and its fixed points. So there is some version of group in between SP4 and SO5 over F2. And that's called Rie or Suzuki group over field of square root of 2 elements. Okay, so we have this Brouillard decomposition, and that's what we're going to study today and on Thursday.
Are there semi-simple groups that are not matrix groups, like spin?
So again, are there what?
So all the semi-simple groups are matrix, are some subgroups.
Linear,
Yeah.
that's what you're saying. They have exact representations.
Yeah. So
Yes.
It's true.
It's a definition, but for example, elliptic curve certainly does not, it's a projective group, so it does not have any non-constant functions, and it cannot be embedded into GLN. So there are non-linear groups, but
They are semi-simple in this sense.
but they're all commutative, for example. Yeah, all the abelian varieties are, all the projective algebraic groups are necessarily commutative. For this very reason, because their joint representation is trivial.
There is a spin group.
Spin is linear.
Okay.
So the theory of compact Lie groups is parallel to the theory of linear algebraic groups. Okay, and well, now we will dwell into the study of those double cosets and I cannot help you with this. So we will, in particular, we will need to introduce some notation to bookkeep the things. So first of all, any double coset like this is isomorphic to the product U. This is this strictly upper triangular unipotent radical intersected W conjugate of the opposite group. Sorry, U minus times B. Okay, and the dimension of this is an affine space, a to the power L, and this L is called the length of W, and it's also the number of positive roots that are conjugates of negative. Yeah, so the roots lie in the Cartan dual Lie algebra by definition. They are eigenvalues, and the while group acts there just because it's the normalizer of the torus, and it preserves the roots just by definition, and that's what I mean. So the while group in this example of GLN just acts by permutations of epsilon I minus epsilon j. Permutations of epsilons, and particularly acts on the roots. Yeah, it takes epsilon I minus epsilon j to some other difference. Sometimes it's positive, sometimes it's negative. And from the point of view of the symmetric group, this is the number of inversions. And also, this is the minimal length of presentation in generators. So W is S maybe I1 times so on S IL, where SI is the permutation, elementary permutation like this, that switches to two neighbors. Okay, so the most general notion is like this. For any while group, there are standard generators, and there is a notion of length with respect to those standard generators, and this holds true in arbitrary situation. Now, this holds true because the intersection of U and the conjugate of U minus is isomorphic to the product over those roots, of the corresponding one-dimensional subgroups. Yeah, so you see that the whole Lie algebra splits into one-dimensional eigenspaces, and each eigenspace generates one parametric subgroup. So each U alpha is just isomorphic to the additive group, and then just you take any order, you take product of this order, and you obtain the whole thing is just a fine space. Okay, so now we are going to construct those double cosets inductively, starting from the simplest ones. The most simple one is just B itself, but then there are the next dimension corresponding to simple reflections like this. So we know that if we take such a simple double coset and multiply it with some other double coset, then we get the next double coset in case the length grows, or else you get two double cosets. Okay. Also, I mentioned those parabolic subgroups, and there are only finitely many of them, and indeed they are all numbered by subsets. Well, so I is the set of simple reflections, or the same as simple roots. So in this case, this set is from 1 to n minus 1. Yeah, first, second, and the last one. And the parabolic subgroups Pj for j arbitrary subset in the set of generators. Say P empty is just Borel, and P the whole thing is just the whole group G, and it is in general Pj is generated by the whole Borel and U minus alpha j for all j's in this subset of generators. Yes?
Yeah, so I do not get how this method inside from the intersection U with omega U minus omega 1, U minus 1 times G with this double coset. What's this map?
Which map?
Is the upper row. Yeah.
Well, certainly it's a subset in here, right?
Why it is subset?
Because it is contained in U, right? By definition, it's contained in U. U is contained in B.
Yeah.
So it is contained in.
Yeah, but then we multiply it to the
Yeah.
What's the right?
Yes. Then we use this. So if we multiply this by W on the right, we get. So I don't see a problem. Maybe the problem is to prove that it's an isomorphism, but at least the map is defined, and well, it really is an isomorphism. But it's certainly not evident that it's an isomorphism. It requires a lot of work.
Okay, and this you already proved that the product of two cosets is in this form.
No, we're going to prove nothing. So it's a quick survey.
But U is
yes.
contained in B.
Oh, certainly, yes. It's the radical of
so
B.
If we multiply U by B, we will get B. No? I mean, you have something that is contained in U. and you
Okay,
multiply it
okay,
by B.
okay. Maybe I should say W times B if you want.
Yeah.
Maybe. Okay. So thank you. Okay. So the whole parabolic subgroup is the union of certain double cosets. And this is just a subgroup generated by those simple reflections. Now, from the fact that the whole group G splits into double cosets, it follows that the flag variety, and in this case, the flag variety is really the flag variety, the variety of all complete flags, right? Because the stabilizer of one complete flag is the Borel subgroup, and there's a homogeneous space, so it has the quotient G modulo B. That's why the name. So this thing is the union of Schubert cells or Breuer cells. So Breuer cell is BWB modulo B. And from this, it's really a cell. It's isomorphic to a to the power L. Okay. But there are algebraic locally closed subvarieties, and XW is the closure of CW, Schubert variety. Well, it's the union of all smaller cells, the smaller in the sense of Breuer order, but maybe let me rather skip this. Also, we'll need the opposite. Say it again? This? Just because of that, but I don't prove it. It's not easy to prove. Yeah. Yeah, but the W is just a point, and then B you quotient out anyway. So we have the opposite cells C tilde. W, they are just B minus W, B modulo B. For example, if W is 1, now this opposite cell will be open. For W equals 1, the cell C1 is just 1 point, but the opposite cell is open in the flag variety. Yes? Pardon me? Well, yeah. Okay. So now what else will we need? We'll need rho is some standard notation. It's 1/2 of the sum of positive roots. Yes. It's also the sum of. Yes, absolutely. It's the quotient Grassmannian, say K planes in n-dimensional space. It's SLN modulo some parabolic subgroup, and this parabolic subgroup is very big. You have J is the whole thing I minus just the point K. Well, it's the complete flags, but there are incomplete flags. Well, J modulo P, G modulo P. This is called partial or parabolic flags.
So the whole J is a group of matrices of
Yeah. So this P will be just like this. So this will be K.
А мы сейчас какой случай рассматриваем? Полный флаг?
Yes. When I write B, I mean the whole flags. When I consider partial flags, I write G mod P. Or maybe I should have written BJ, something like this. Oh.
This all the supercells, other as a motion to the usual one. I mean, maybe you just twist omega by the longest root.
Yeah, certainly, yeah. Longest, it's not omega but W, and you multiply it by W naught, yes, by the longest element of the while group. Let me, so these are fundamental weights. While we're at weights, there is the notion of dominant weights. Just a monoid or cone of dominant weights, and given an element here, we consider the character lambda, or maybe from the Borel subgroup to the torus. There is just Borel modulo its radical, and then to the multiplicative group. So this is lambda. Given this character, well, we have one-dimensional representation of the Borel subgroup. Given any representation, B representation V, we consider the corresponding associated vector bundle say V. This is G times V modulo the diagonal action of B. So it's the set of pairs G, V, modulo the relation that G, V is equivalent to G, B inverse, BV.
This is just an induction.
Yes, the associated vector bundle. So it's a G equivariant vector bundle, and the stabilizer of any point, well, it's a vector bundle over the flag variety. The stabilizer of any point acts on the fiber at this point, and if you take the point corresponding to B itself, then the fiber is canonically V itself, and the action is just this tautological action. And so I must stop, yeah, and I will stop in 2 minutes. Just let me say that for dominant weight lambda, we associate L of lambda, or maybe also O of lambda, line bundle on the flag variety associated to the representation negative lambda. So by definition, the positive roots are those in B. Yeah, and for example, if you take SL2, so that the flag variety is just P1, yeah, then L, well, and the x plus of t is just natural numbers, yeah, torus is just one-dimensional. T is a multiplicative group, and all the characters are just integers. T goes to t to the power n, and among them there are positive ones that correspond to the roots inside B. But the roots inside B, they correspond to negative line bundles, like cotangent line bundle, for example. And the roots outside of B correspond to positive line bundles. And that's why it's such a strange notation. L of lambda corresponds to negative lambda, because I want L of lambda for positive lambda to be a positive vector bundle. Okay? And then if not now, with such notation, there will be some global sections. So the global sections of B with coefficients in O of lambda it is called maybe let me dualize, and then this will be V lambda. So it's a G module with highest weight lambda. If I didn't dualize, then this would have lowest weight minus lambda, just by definition.
The fiber at B
Yes.
is isomorphic to this, maybe dualized, but then why is it the global sections are
No, this is just the definition. We would define V lambda as the dual space of sections of this line bundle. Okay, and we will. The point of our study for next couple of weeks will be a computation of character of this representation. So in characteristic 0, this will be an irreducible representation. In characteristic P, it's not irreducible. In general, it's called Weil module because character is given by Weil character formula. And we will deduce this eventually.
So this space of global sections is actually a representation of a...
Yes, just because the vector line bundle itself is G equivariant, so G acts on the global sections. And this is our primary object of study, but just one last word. I say that this line bundle O of negative 2 rho, for example, under this notation is the dualizing sheaf, a canonical line bundle of the flag variety. For example, for P1, O of minus 2 is omega P1. Okay, and rho is this. And in fact, this is just a tautology. Because we know that the tangent bundle, to flag variety, say its fiber at B, is just G modulo B. Yeah, because homogeneous space. So the tangent bundle is this, and so the eigenvalues in the tangent direction are all negative roots, and then when we take the determinant of the dual bundle to obtain the canonical line bundle, we obtain the sum of all positive roots, but with our notation with minuses, this corresponds to negative 2 rho. So let me stop now, and I will not repeat any of this next time, because it will take me another half an hour to an hour. So I will just start from this point on. I will not repeat any of these notations. So you are very welcome to never attend all the remaining classes. But if you choose to attend, then please learn by heart all the notation.